In this video, we'll continue our discussion of omitted variable bias. Our discussion will be based on a new economic example. And in this example, we will discuss the labor supply decisions of mothers. In this example, we'll discuss the setting that is discussed in a seminal economic research paper, which is called Children and Their Parents' Labor Supply Evidence from Exogenous Variation in Family Size. It was written by Josh Angress and William Evans. It was published in 1998 in the American Economic Review. To explain the research question, let's think about moms with two children. So there is a woman, and she has at least two children. Let's start with a mom with exactly two children. In our discussion, we'll assume that the mom and her kids are part of a heteronormative family, so there's probably a dad in the background, but we're not really interested in him, so let's just ignore the dad. As I've explained, we're only looking at families with at least two children, so we'll have families like this one with exactly two children, but we'll also have families with more than two children. So let me draw a family with three children. Now let's define a new binary variable or dummy variable that is called more kids. And it takes the value 0 for all the families that have exactly two kids. The variable more kids takes the value 1 for all the families that have more than two kids. More kids is our variable of interest. That is, we want to study how the behavior of a mother changes when she goes from having exactly two kids to having more than two kids. The behavior that we are interested in is labor supply. So we have an outcome variable. It is called weeks worked, and it gives the number of weeks the mother worked during the year where she is observed in our data. When labor economists study labor supply, they distinguish between the extensive margin and the intensive margin. And the extensive margin describes whether someone works at all, and the intensive margin describes for those who work how much they are working. Weeks worked is a measure of the intensive margin. Let's suppose that we have data on our variable of interest and on our outcome variable. We can put this observed data into a scatter plot. Let's put more kids on the horizontal axis and weeks worked on the vertical axis. More kids is a dummy variable and can only take on the values 0 and 1. So all our data will be located on these two lines. We'll observe some mothers with exactly two kids and some mothers with more than two kids. Let's denote the number of observations with more kids equal to 0 by n0 and the number of observations with more kids equal to 1 by n1. Clearly, if we add these two numbers, then we will arrive at our overall sample size n. Let's regress our outcome variable weeks worked on our variable of interest more kids. This is a simple linear regression with only one regressor. So in our OV bias framework, it corresponds to the short regression. We know that the estimated causal effect beta 1 hat is given by the sample covariance between the outcome weeks worked and the regressor more kids divided by the sample variance of the regressor more kids. Now we can use the fact that more kids is a dummy variable, so it takes only the values 0 and 1. We can use that to rewrite this expression into a much simpler form. First, we take the sample average of weeks worked for all the observations with more kids equal to 1. So we're taking a sample average over all these points. And then we subtract the corresponding sample average over these observations. We can also rewrite this using a variant of our special notation for sample means. So we can write this as the sample mean over weeks worked. But, and now this is new, only on the subsample where we observe more kids equal 1. And then we subtract the sample mean of weeks worked, taken on the subsample where we observe more kids equal 0. In a large sample, these two sample quantities will be close to the corresponding population quantities. So this will be approximately equal to the population expectation over weeks worked on the subpopulation with more kids equal 1 minus the population expectation on the subpopulation with more kids equal 0. This shows that this estimator is estimating this population quantity. But how do we interpret this population quantity? If it is equal to the causal effect beta 1, then we are good. But if it's not, then we should think about what it is that we are estimating. So we are comparing the average mother with more than 2 kids to the average mother with exactly 2 kids. How are these two average people different? Well, first off, mothers with more than 2 kids have more kids, so they have 3 or 4 or 5 or even more kids rather than just 2. We suspect that this difference will impact their weeks worked. And this is in fact the causal effect that we are interested in. So we're interested in the causal effect of passing from 2 kids to more than 2 kids. Likely this causal effect will be negative, as a mother with more kids has to take over more childcare duties and has less time to work or to apply for jobs. But the average mother here may also be different from the average mother here along other dimensions. Suppose, for example, that some families live very close to a grandparent. This grandparent may be available to take over certain childcare duties so that the mother has more time to pursue activities other than looking after her own children, such as looking for work or working. We could find such a grandparents in families with more than 2 kids or in families with exactly 2 kids. But where would we be more likely to find such a grandparent? Well, maybe for families down here. And that is because people plan ahead when they decide how many kids they want to have. So a couple who knows that they can count on a grandparent to take over childcare duties in the future may be more willing to decide on a large number of kids rather than having only 2 kids. Let's describe grandparental childcare by a new variable. Let's call it weeks care, and it gives the number of weeks in a year with free childcare. Now, when we observe different average weeks worked in these two populations, then we don't know whether this is caused by the causal effect of more kids or whether this is caused by unequal distribution between the two populations of this week's care variable. A variable that makes it hard to deduce a causal effect from a between groups comparison is called a confounding variable. Let's look at the joint distribution of our variable of interest and the confounding variable weeks care. We'll put our variable of interest more kids on the horizontal axis and our confounding variable weeks care we'll put on the vertical axis. More kids only takes the values 0 and 1. So all of our data will realize on these 2 lines. Before we proceed to fill in this graph, let's remind ourselves of all the facts that play a role in this economic environment. We have our outcome variable weeks worked, and we have our variable of interest more kids. More kids has a direct causal effect on weeks worked. This is our effect of interest. Then there's also the confounder weeks care. And weeks care also has an effect on weeks worked. And this is because the more free childcare a mother has access to, the more she can work. Let's also remind ourselves of the fact that the slope coefficient beta 1 hat estimates this population feature, where this first expectation is over the subpopulation of all mothers with more than 2 kids, and this second expectation is over the subpopulation of mothers with exactly 2 children. If I'm looking at the average mother with 2 kids, I know where to place her in terms of more kids. More kids equal to 0 for her, but I don't know where to place her in terms of weeks care because this is unobserved to me. We argued previously that more kids in weeks care are correlated. In fact, we argued that it is plausible that there is a positive correlation between those 2 variables. This correlation can come about in different ways. For example, a couple may observe the amount of weeks care that is available to them theoretically now and then decide how many kids they want to have, or they may, for example, decide that they really want to have lots and lots of kids and then move closer to their parents to increase the weeks care that is available to them. So the direction of causality could go this way or both ways. Now, if my economic reasoning is correct, then I should put the average mother with 2 kids here in this diagram, and the average mother with more than 2 kids, I should put up here. The causal effect of more kids on weeks worked is called beta 1, and we suspect that it is negative. We define causal effects as ceteris paribus effects, so the causal effect of more kids is changing only the variable more kids and leaving all other factors unchanged. So for our mother with just 2 kids who sits here in this graph, if she's thinking about a causal effect of changing more kids, so of having 1 additional child, then she's thinking about moving into this direction. She thinks about changing only more kids, but not changing weeks care. A ceteris paribus change for her means moving horizontally in the diagram. Comparing weeks worked of the average mom with more than 2 kids to weeks worked of the average mom with exactly 2 kids would give me the causal effect of weeks worked if I had placed the mom with more than 2 kids here in weeks care and more kids space. But because of the correlation between more kids and weeks care, I didn't. Therefore, this comparison not only captures the causal ceteris paribus effect, but also the effect of the average difference in weeks care. That is, this effect. Therefore, comparing these 2 populations corresponds to moving diagonally in this graph. Beta 1 hat doesn't estimate the effect of changing 1 single variable. Instead, it estimates the combined effect of changing 2 variables at the same time. First, changing more kids from 0 to 1, and changing weeks care from the level that is typical for the more kids equal 0 population to the level that is typical for the more kids equal 1 population. Let's call the effect of weeks care beta 2, and let's assume it's positive. In that case, this difference here is guaranteed to be larger than the causal effect beta 1 that we want to estimate. We can analyze this problem also in our framework for omitted variable bias. Our formula for omitted variable bias says that the OLS estimator beta 1 hat is approximately equal, at least in large samples, to the true causal effect beta 1 plus the covariance between the regressor and the omitted variable, and the omitted variable in this case is weeks care, divided by the variance of the regressor times the effect of weeks care beta 2. Now, this expression looks similar to this expression, and we can rewrite it in the same way. This is the difference between the average level of weeks care in the more kids equal 1 population and the average level of weeks care in the more kids equal 0 population. This difference is equal to the blue arrow in this graph. Multiplying this difference by beta 2, or in other words, this part of the formula, gives us the omitted variable bias. We believe that beta 1 is negative, And for the OV bias, we are multiplying something that is positive by a positive effect. So the OV bias is positive and will move us into this direction. So for example, we may estimate this effect, and indeed beta 1 hat will be larger than beta 1, just as we have already argued here. In this video, we have gained a new intuition for OLS. We have learned that OLS essentially sorts observation into two groups according to the values of the regressor, and then compares the average outcome across between the two groups. OV bias can occur if the two groups differ along other dimensions other than just the regressor. And this can happen if there is a confounding variable, like there was weeks care here. In that case, beta 1 hat will not measure just the effect of changing the regressor, but the combined effect of changing both the regressor and changing systematically the value of the confounding variable.